Section 4.2 is called sums and sigma notation, and we're going to encounter some notation here that's going to feel like it's sort of a deviation from what we've been doing with antiderivatives. But if you'll just bear with me for a couple of sections, we'll put it all back together and you'll see how it relates. Okay? So to start with, we've got this idea called sigma notation. Sigma notation is a way of expressing the sum of a bunch of things in a condensed way. So if we had the values a1 to an, and these are just numbers, that's all they are, is just numbers, and we wanted to add all of them together, we would have to write them like this. Right here, a1 plus a2 plus a3 all the way up to an, however many of them there were. The condensed way of writing that is to use this sigma notation. It's a Greek letter. It starts with I equals 1, and it goes up to I equal n of the a with the subscript of I. I is called the index of a summation. A sub I is the ith term. It's just the term that we're on. And then the upper and the lower bounds on the summation are n and 1. So the n is on top, it's my upper bound. The 1 is on the bottom, and it's my lower bound. It tells me where I start and where I stop. All right, so we're going to do an example of one. We've got this summation notation. It tells you at the bottom that it starts at I equal 1, right? And it tells you that it stops at 6. That's like saying I equals 6 on top. And what we have is we have this expression 3i minus 2. And the I here is not the imaginary unit I or anything like that. It's just like an x. It's just a variable, okay? So what we're going to do is we're going to write out all of our terms. a1, a2, a3, a4, a5, and a6. Why do I only need up to a6?
Because that's your range.
Yeah, because the lower and the upper bounds tell me where to start and where to stop, right? So make sure you're paying attention to those so you don't get more than you need or fewer than you need. And all you're going to do is you're going to plug in the values 1 through 6 into the I value in the 3i minus 2. So on the first one, that would be 3 times 1 minus 2, which would give you 1. Okay, so we're going to go down this list. I'd like for you to go ahead and fill these in. I'll do the second one with you again. So we'd be doing 3 times 2 minus 2, which would give me 4. 4 is correct. Go ahead and go down with the A3, A4, A5, A6. Fill those in, and then we'll make sure everybody has the same values for those. Okay. So find those 4 more values and write those down. What'd you guys get for A3? 7. How about A4? 10. A5? 13. And A6? 16. And did anybody notice a pattern once you started going and you didn't actually really plug them in? Yeah, they're increasing by 3 every time, right? Any idea from the equation why that's happening? Why is it increasing by 3 every time? Do you see a 3 in the equation? Yeah. That 3 in the equation is what's, well, when we work with it in a different context, we call it the slope. And it tells you how quickly something's increasing. So for every increase of x by 1, it increases y by 3. So that's why that's increasing by 3. So finding the sum is simply adding these values together. So we're adding 1 plus 4 plus 7 plus 10 plus 13 plus 16. And what do you get? 51 is correct. So this is just arithmetic, right? This is not calculus. Agreed? Okay. Just arithmetic. You're just evaluating and you're adding things together. And this works fine and dandy as long as you weren't having to evaluate this for too many values, right? If this went from a equal 1 up to a equal 100, I don't think you'd be near as happy about it. Agreed? But for a few terms, it's not bad. You can compute it very quickly, even if there is a complicated term. Like this one's really simple, 3i minus 2. But if you had something squared or something like that in there, it might take you a little bit longer to do it, but it would still be manageable. Now, it doesn't always end up being manageable, again, if you had too many terms. So there's some methods for making this a little bit easier. So there are some summation formulas that will allow us to make that a little bit simpler. So if we have n as any positive integer and c as any constant, and we have these, there's 5 of them, 3 of them are on this slide. Any of these 3, they actually simplify to a condensed form, a simplified form that we can use. So on the first one, this one's called a sum of constants. If you have the c value, add it together n times. So imagine that this said, so this isn't a proof for it, but it's to give you an argument for why it works. Imagine this said from I equal 1 to 6 of 5. Well, it would mean that A1 is 5, and A2 is 5, and A3 is 5, and A4 is, they're all 5, right? So you'd have a bunch of 5s added together. How many of them? 6 of them. So this would be c times n, exactly. So the condensed form, a way of computing this, if it's just a plain old constant, is to take c, whatever the constant is, I gave you an example with the number 5, times n, the number of terms. Now, again, that's called the sum of constants. That's written in your notes. The others I'm not going to show you details for. They are in your book if you're interested in seeing where the formulas are coming from. The second one here is adding together from 1 up to wherever you end, because this is just the term I. It's like having x in here, right? So the first term is 1, and the second term is 2, and 3, and 4, and 5. So you're just adding up the numbers from 1 to n. So this is actually going to give you a formula that looks something like this. However many terms you have, you multiply that by the term that's one more. So if you had 6 terms, it would be 6 times 7. And then you divide that value by 2. And that tells you the sum of the first n integers, however many of them you had. Number 3, this one's squared now, right? And it's going to look similar to number 2, but there's sort of an extension of that. So you're going to have an n and an n plus 1 in the numerator. You're also going to have an 2n plus 1. And it ends up being divided by 6. This is the sum of the squares. So you have things like 1 plus 4 plus 9 plus 16 plus 25, all the squared terms added together. And you can condense that by writing out n times n plus 1 times 2n plus 1 over 6. All right, a couple others, and these are really nice general rules, and they're going to feel a lot like things that you've done with derivatives and now antiderivatives as well. When you have a constant multiplied by the term a sub I, you can pull the constant in front. So you could write this as c times the summation from I equal 1 to n of a sub I. No matter what the a sub I term is, you could pluck out the constant and put it in front. We've done that with derivatives and antiderivatives, right? And limits for that matter, too. So this is not a new concept. And again, on number 5, it's the same kind of thing, again, you've seen with derivatives and antiderivatives and limits, is that if you have the summation of the a sub I and the b sub I, you could separate it out as the summation of each of them individually. So you can write this as the sum from I equal 1 to n of a sub I plus the sum from I equal 1 to n of b sub I. All right, so the next examples that we're going to take a look at are going to apply those features. All right, so the first one has 16 terms. It's sort of on the borderline. I mean, like, we could do 16 terms. It wouldn't be the worst day in your life. I mean, you could do that. But it's certainly not 6 terms. So we're going to use, and the directions tell us to anyway, to use summation rules to compute this, excuse me. So as you're taking a look at what I'm going to show you, this is exactly what I expect to see when you're working the problem out, okay? You're going to actually write out, using those summation rules, this all spread out. So you'll notice one of the issues right here is that you've got 2 pieces that are subtracted. So we're going to separate those as to 2 pieces that are subtracted. And then you'll also notice that this number, 5i, has a 5 in front of the I. It's a constant. We're going to pluck the 5 out in front. So you can do both of those steps at the same time if you'd like, so that you're plucking out the 5 of a sub I, of I, and then you have subtracting the I equal 1 to 16 of 4. Does that make sense? You're just separating everything, and you're going to do that on each one of these problems. You're going to separate them. Now, the first one has this times 5 business, but it's a summation of I, and there is a rule for doing that. Which one was it? 1, 2, 3, 4, or 5? Did you see it? It's 2. And it says, what am I supposed to do? Well, I'm supposed to multiply n. What is n in this problem? 16 times what? 16 plus 1, so 17. Divide that by 2. Okay, so that's the first piece. So all of this became this, right? And then we've got minus. Now, summation of the number 4. Which rule is that? That's the constant one. That's number 1. So that says that I should multiply the number 4 by what? 16. And then it becomes just arithmetic as well. So you can grab your calculator, multiply, divide, add, subtract, simplify. $7.44. Did you add at the end or did you subtract, Luke? I think you're supposed to subtract. But you're close. You've got the right values before that. So if you subtract, what do you get?
If you subtract.
What was it?
I got 616. Yeah, me too.
616. Good. Is everybody getting 616 on that one? Okay, great. All right. Same thing on the next one, but I want you, before you start, to notice there's 2 things that are different about this problem. So somebody give me what you see is different. Okay, so one more time, what?
N is a lot bigger.
N is a lot bigger. I didn't even think about that one. So there's 3 things. N's a lot bigger, you're right. What else did you come up with, Chancellor?
So there's 2 N's?
There's 2 N's inside there, and so we're going to need to simplify something inside before we apply any of our rules, right? Okay. I think what you mean is that there's an N right here and here. Is that what you mean?
Yes.
Or is there 2 N's
Well, I meant
here?
I meant there.
Okay, then I was interpreting what you said right the first time. So one of the things here is we're going to need to simplify this before we start. There's something else. There's an N instead of an I. That's what I was mentioning here just a second ago. That's true. That doesn't actually affect anything. That N versus I is just a dummy variable. It's like having an equation with an X in it versus having an equation with an S or a T in it. That doesn't really affect anything. It looks a little weird, though. There's something crucially different, though.
We're not starting at 1.
We're not starting at 1. That's really important. Do you see how this says n equals 4 is the starting point? Look back at your rules. All of your rules hinged on starting at n equal to 1. So we're going to have to actually do something different because n starts at 4. Okay? So let's deal with the fact that this has the expression sort of in factored form first, and then we'll deal with the n equal to 4 after that. So the first thing we're going to do is we're going to write out that this is going from n equal from 4 to 140 of n squared minus n. Is everybody good with that so far? Okay? So the n in our problem here is acting like the I did in all of those equations. That's fine. It's just a different letter. If it really bothers you, turn your n's into i's. I'm going to be fine with that too. I don't care. All right? So I can separate this using the rules that we had before. So this is the summation from n equal to 4 of 140 of n squared minus the summation from n equal to 4 from n equal to 4 to 140 of n. Okay, so I can use the rules and I can, plug them in, except that they're going to be off because I don't have n equal to 1, n equal to 2, and n equal to 3. I don't have those terms in my sequence. Any idea how to compensate for that?
Divide by 3?
No, but you're getting close. Do you have an idea, Luke?
Well, I'm not sure if this would be the easiest way to do it, but you could just plug that in and find out what that value is, and then do a separate one, n equals 3, or n equals 1 and do it from 1 to 3 and then subtract that.
You're getting really close. I heard you say something for me, though. Someone
that
over
not
here
work,
said, it will, but there's a simpler way to do what you just suggested at the very end. Somebody said subtract. Who said subtract? You said subtract. I heard it on this side of the room. What did you want to subtract?
4 from 3.
You're getting close. That's not what we want to subtract, though. Okay, so those summation formulas take A1, A2, A3, all the way up to AN, right? And we're missing exactly these three terms in our sequence. Agreed? We don't have A1, A2, or A3. Can you find A1, A2, and A3? How? Yeah, plug in 1, 2, and 3. So you could actually figure out what is A1, what is A2, and what is A3. And then what could you do? Subtract those from what you want. So what we're going to do over here is we're going to actually do this same expression. I'm going to change this so that it starts at n equal to 1, because that's what I need it to do in order to be able to use those formulas. And then I need to subtract off A1, A2, and A3. Does everybody make sense of that? Because when I find these two summations right here, it's going to include A1, A2, and A3, and they shouldn't be included. They're not in the sum that I'm working with. So I'm going to calculate them, and then I'm just going to remove those values from what I'm working with. All right, the n squared one. What do I get? How do I get that one?
140 times 121 times 280.
1, right?
1, 6.
Uh-huh. All right, so we'll do the first one. Somebody else do the second one for me. This one. What am I going to multiply on top? 140?
Times 141.
Good. Good. And then we need to subtract off A1, A2, and A3. Sorry, what was that? 8 for all three of them? Did you calculate all three of them for me? Okay. So tell me, just to make sure everybody's on the same page, what did you do to find A1?
So you plug in 1 for that and you get 0.
Okay, so you plugged in 1 right here and you got 0.
Right.
Yep. And then,
2 and you get 2.
okay.
And then you plug in 3 and you get 6.
Okay, so you had 0, 2, and 6, which is a total of 8. So we'll subtract off 8 when we're done. Good. All right, your calculator is your friend for this one, the rest of this one. Add, subtract, multiply, divide. What's the summation? It's big. So
I got 914,612. That's right.
that's what I have, so I hope so.
Okay.
Do I have a second on that? Or third, I guess, because you and I did the first and second. So a third?
Yeah.
Yeah, I've got a third and a fourth and a couple more nods. All right, so we get 914,000 and some change. All right, any questions on the processing of doing this? Okay, so what we're going to do next time is we're going to take this notation and we're going to put it into how the graph looks and how that's using the graph to, what the graph is doing when we're doing this summation notation. And then next Thursday, when we come back to it again, we're going to combine this idea of summations with your idea of antiderivatives and show you how they're connecting. Okay? All right.